Yes, thank you for having me, and thank you for the attention. Hopefully there's something interesting. Me and my team had, our original study was to look at what happens when we add computational things, visualizations and coding into introductory physics courses to understand if we could affect learner outcomes in actual knowledge acquisition. So this was a four-week-long physics class that was online, open to global learners. And we were intervening in each one of the week's homework assignments by adding some type of a different intervention. So some students did math by hand, some students coded math, some students had been given interactive visualizations that they could play with. And we cohorted them, we added them into a group, and they went through all 4 weeks getting one particular type of intervention. And then we tried to study if any one of those groups did differently. I'll tell you up front, we didn't get statistically significant results, but I still think we learned an incredible amount about how to manage such experiments, including the fact that in online courses like this one, students can enroll after other students. So once the course has begun, somebody can come in week 2. They still have to complete the earlier weeks, but we need to have already cohorted everyone who enrolled in week 1. So this on-the-fly cohorting in order to randomize the groups was something that we put a lot of effort into. And if you want that knowledge transfer, reach out. We can help you understand how to keep valid experimental design in an actively enrolling study. So here are some little visualizations. Everything is in inverted color, perhaps because I use my computer in inverted color. So forgive the strange colors if it's uncomfortable. So on the left, it was just coding challenges that some groups were given. On the right, it's a interactive visual thing. So it's some type of a plot or an animation. On the bottom right, there's a non-visual interactive component. So this is like a table of numbers that changes as you move sliders. And on the very bottom, in order to manage time on task and to normalize whatever confounding factors we can, we gave some students some thought experiments. Just think about these things. Don't do math, don't code, don't look at interactive things. Just think about this stuff. So we used a 2x2 factorial design in order to study this. We had a control group that did standard physics problems, a group that got programming and visualization, a group that got programming and non-visual interactives, a group that got the questions to help people think about the problems, and visualizations and questions and non-visualization. Here are the results. The stars that you see here are things that I think are interesting that should be explored more, but they are not statistically significant. So so down the very far left column, you'll see the groups. In the top, it's the actual conditions that I just talked about. And then each one of the columns to the right is their score on a standardized assessment that's been vetted and proven to be at least trusted and accepted by the community as a measure of one's physical understanding of the world, one's spatial intelligence, or one's understanding of computer science. The 2 stars that are on this top pane I find kind of interesting. So the programming seemed to help, the programming and the non-visual seemed to have not helped as much with spatial understanding, which would make sense. There's no visualization. Nor no conceptual visualization in the mind due to pondering questions. And the questions and the visualization seem to have helped with computer science, which is pretty meh. That's why it's not statistically significant. So these are the dangers of these numbers. So luckily we've run our ANOVAs and we know that they're not statistically significant, but I will always like to point out that even when things look interesting, you know, look behind the hood. Yes, so visualization, if we group the 2 groups that had visualization to normalize out the programming part, it seems like that may have had some slightly bigger impact, although not statistically significant yet. Our numbers were smaller than expected. on physics and spatial comprehension, spatial intelligence. So I don't know, it's something, it's promising. We at least have some machinery working. And then if we look at the learning outcomes of the students in the actual course, the thing that gets a star as interesting but not statistically significant is that the questions and the non-visualization, so the sort of the least engaging of our interventions, as an educational designer would say, seem to at least show some minor signal that may have been the most effective on course outcome, maybe because it gave time for students to do other things, like spend time working on their P-sets and homework problems. So it's something to consider as you intervene in educational systems. Are you drawing time away from other tasks that might actually be helpful? And the last thing I wanted to close on is that I have some other ongoing related things. So I've been using artificial intelligence to analyze the discernibility of tactile graphics for visually impaired blind learners. I've been sonifying data in order to help make multimodal, more engaging versions of black hole simulations. I've been producing some 8-channel spatialized audio, mostly for wonderful social emotional learning and engagement, especially at the end of the pandemic, and comparing some human psychophysics of facial recognition under non-ideal situations to artificial intelligence systems. If any of those pique your interest, feel free to reach out and I'd be happy to chat. All right, thank you so much.